A 40-gram bullet accelerates from a dead stop to 90 meters per second in a fraction of a second. Taken on its own, this looks like the sudden creation of motion. But in a physical world where every effect requires a cause, we have to account for where this massive forward push actually came from. Physics tracks motion using a ledger system. If the starting balance is zero, the final balance must return to zero. You cannot simply create momentum out of thin air. The perception that we've broken the rules of physics only happens because we're looking at the bullet in isolation. We are focusing on one half of a two-part transaction. To find the missing balance, we have to widen our view and draw a boundary that captures every interacting part of the firing. This boundary defines an isolated system. Inside this box, we assume no external forces, like friction or the grip of a hand, can influence the objects. By sealing the system, the only forces allowed are internal ones, the mutual pushes and pulls occurring between the gun and the bullet itself. This boundary is a tool that allows physicists to close the books. It ensures that every trade of motion can be tracked without outside interference. With the system isolated, we can run a precise audit on the forces that occur during the ignition. Inside the chamber, the expanding gas of the propellant pushes violently in every direction. Following Newton's third law, the gas pushes the bullet forward with a force F. Simultaneously, it pushes the gun backward with an equal and opposite force, negative F. Since these two objects are pushing off of one another, the time they spend in contact, delta T, is identical for both. Newton's second law tells us that a force applied over a specific time creates a change in momentum. Because the forces are equal and opposite, and the time is the same, the resulting changes in momentum are also perfectly mirrored. As we see in this derivation, the bullet's momentum is exactly canceled out by the gun's recoil momentum. When you add them together, the total is still zero. The forward motion of the bullet is perfectly compensated by the backward recoil of the gun. The system's total momentum remains exactly what it was at the start. This same accounting applies to objects that are already moving when they interact. This diagram shows two spheres, A and B, before they collide. Each carries its own initial momentum, which we record as the starting balance of our ledger. During the impact, they trade momentum through equal and opposite internal forces, just like the gun and the bullet. After they bounce apart, their individual velocities change, but the total amount of momentum across both spheres stays constant. This equation is the master ledger for all mechanics. It shows that the total final momentum of the system must equal its total initial momentum. Momentum acts as a currency. It is transferred from one participant to another, but the total amount within the system is never spent. This rule holds firm regardless of how destructive the interaction becomes. In an inelastic collision, objects crumple and stick together. A massive amount of kinetic energy is lost as they deform. Heat and sound might drain the system's energy, but they cannot change its momentum. In any isolated system, the total momentum remains a constant value that does not waver. While individual objects may speed up, slow down, or shatter into pieces, the total momentum of their interaction remains perfectly and permanently balanced.